Okay, I'm going to kick things off by talking about basically the three ways that we understand whether particular trends are related to climate change. And I'll discuss briefly three examples of extreme weather that we care about, whether climate change is playing a role in them. And the three ways are basically, can you tell if there's a trend in the data? Is there enough data to be able to detect a trend? Do climate models predict that a trend should exist? And is there a good physical reason for such a trend to exist? So if you have a good physical reason to expect a trend, but there's no trend showing up in the data, models don't predict one, then there's probably not climate change effect going on. Any one of these three is insufficient evidence. 2 out of 3 is pretty good. 3 out of 3 is very solid. And you care about not just the existence of a trend, but whether the magnitude is appropriate as well. And these concepts are explained in a lot more detail in the National Academy's report that came out a few years ago on extreme weather events and climate change attribution. And they discuss not just these concepts, but basically the full set of types of extreme weather and the extent to which we can tell whether they're related to climate change. So the first obvious trend is warming temperatures. It's called global warming for a reason. And most of the graphs on the left-hand side are graphs of global average temperature, except the dark red one is Texas average temperature. I've averaged it over 9 years rather than just showing annual values because there's a lot more noise, there's a lot more weather on the local scale. Things tend to average out if you look at things globally. But you can see that overall, there's a similar trend in both global temperatures and observations. And actually, the smoothest line on the graph is the average of climate model simulations of historic conditions. So we have clear historic trend, we have climate models projecting a trend or simulating a trend, and we have a sound physical reason to expect a trend by reducing the amount of emissions of radiation to space. We affect the energy balance and through greenhouse gases, lead to warmer temperatures. And you can see from the map on the right that these temperatures are going up really throughout the state of Texas. It's not just an urban heat island effect or something like that. And looking more closely at maximum and minimum temperatures, the average across the state of Texas, each dot here represents a year going back from 1895 to the present. And the trends basically were fairly flat for most of the 20th century. The 1970s and 1980s were actually the coolest decades in Texas, but temperatures have been trending upwards since then. As you can see on this graph, they've been trending upwards faster than the global average. And the expectation from climate models is they would go up about 20% more rapidly than the global average temperature. But average temperatures don't tend to have much effect on things. What tends to matter is the extremes. So here I'm looking at the hottest temperature of the month for the months of June through September in the upper left. And similar shape as before, except temperatures are not dramatically warmer than they have been in the past century. They're just barely above the long-term average. So the peak heat has not risen as much as the average temperatures. If we compare that plot to the average temperatures, the biggest difference is really the size of the decline from the 1950s to the 1970s and 1980s. Since the 1980s, temperatures have been trending upward at the hottest temperatures, just like they've been trending upward with the average temperatures. So I think what's been going on there is probably the large increase in irrigation and surface water that took place after the drought of the 1950s that basically provided some quasi-natural air conditioning for the Texas land surface. The coldest temperature of the year has generally trended upward. We're, as with these other numbers, warmer than we had been on average during the 20th century. You can see a few small dots at the bottom of this graph. Particularly 2021, reached the third lowest average temperature across the state of Texas in recorded history. 1899 is the dot in the lower left. 1989 was pretty cold also, as well as 1950. But you can see that the trend is upward. So based on historical data, we expect the trend in extreme cold temperatures has been rising to become milder. Climate models also project milder winter temperatures. And the physical basis for that is that the Arctic is warming even faster than the rest of the globe, and that's where we get our cold weather. Now, you may have heard from news coverage that climate change is making this sort of weather more likely, and I'll explain that apparent contradiction in a minute. First, I want to put them both in the same scale. Each one of those horizontal lines is 4 degrees difference, and what you can see here is that the winter is much more variable than the summer. On the extremes, you can expect the average hottest temperature across Texas to be around 100 degrees, give or take a few degrees, whereas the coldest temperature can be anywhere from 20 degrees Fahrenheit to 0 degrees Fahrenheit. And that's what makes dealing with winter so challenging in Texas, because you never know quite how cold it's going to get. The challenge in the summertime is you know it's going to get hot, and you have to endure that. Here's how cold it got in February 2021. This is average temperature hour by hour in Texas for the middle of February. And temperatures really plummeted on the 15th and 16th. The average Texas temperature got down to about 8 degrees Fahrenheit in both those cases. Obviously colder to the north, warmer to the south, but every place in the state managed to get down below freezing and even have an entire 24-hour period below freezing, except for some places along the immediate coast. Here's one more way of looking at those cold temperatures. This is the daily average minimum temperature across Texas, again starting in 1899. And each one of those dots is an individual day. This plot sort of looks like icicles because it gets cold in the wintertime and it's warm in the summertime. So these vertical lines every year. And you can see how cold it got in 2021 over on the right-hand side, the coldest since 1989. And in fact, it was 8 degrees or 9 degrees colder than in any day since 1989. It had not gotten below 16 degrees Fahrenheit on average across Texas since 1989. And that is the really unusual part of this time series. It happened relatively frequently in the 20th century, and it's been quite rare since then, actually even more rare than would be predicted from climate change. So I think in part Texas lucked out in having that gap in extreme weather. Of course, it meant we didn't know what was going to happen exactly when it did come along. The blue lines are the average maximum temperature, and actually the average daily maximum temperature on the 15th in February 2021 was about 21 degrees across the state of Texas, and that's the coldest average maximum temperature across the state ever recorded. The only comparable times were December 1983 and January 1985. And another unusual thing about that weather event was the widespread snow. Each one of these circles represents the amount of snowfall during the 4 largest snowstorms in Texas history in terms of area and amount. And the dates are February 1895, January 1926, December 1929, and February 2021. It's hard to rank these four. They're basically clearly larger than any of the other snowstorms in the state. And it is remarkable that one of the coldest periods in the state of Texas was accompanied by one of the largest snowstorms in the history of the state of Texas also. It's not unusual for northern parts of the state to get snow, typically a foot or more during the wintertime, but in the lower valley, of course, it's almost unheard of. So it's kind of difficult to talk about a typical Texas winter when the color of winter is quite different in different parts of the state. Okay, I mentioned a bit of an apparent conflict about weather, climate change, and how it was affecting cold temperatures. There's basically two different types of effects. The technical terms for them are thermodynamic and dynamic. The way I like to think about them is the way things are and the way things behave. So an example of the way things are, warm air holds more water vapor. So given warmer temperatures, you expect the atmosphere to have more water and be able to produce more intense rainfall. Another example that matters for what I was just talking about, the Arctic's warming faster than the rest of the globe, so that should make our winter temperatures milder, everything else being equal. Dynamic refers to the way things behave. So it's not just temperatures changing things directly, but it's also temperatures potentially changing weather patterns, potentially changing the structure of weather systems as well. So for example, because of climate change, we expect that the maximum intensity of hurricanes is increasing, and so that's going to affect how long heavy rain from landfalling hurricanes can persist, for example. And that's on top of warmer air holding more water vapor. For cold, there's been studies that show that Arctic sea ice loss can actually make the stratospheric polar vortex less well-behaved and lead to more frequent weather patterns that associated with cold air in Texas. So the weather patterns may become more common, and now we've got these two competing effects. The warmer temperatures leading to milder weather in the winter, but the weather patterns leading to more frequent cold air. The way that sorts out, according to the literature and the IPCC, is that the thermodynamic effect is larger than the dynamic effect in this case, so that even though the weather patterns may become more common, it'll still be milder when it does get cold in Texas. And again, the magnitude of the overall trend is actually similar to the magnitude of global warming trend as well, which is about 2 degrees of warming so far and another few degrees going forward. Of course, go back to that plot of winter temperatures in Texas. A few degrees of warming really doesn't make a whole lot of difference. It still can get extremely cold either way. Okay, another type of extreme weather is drought. And this is the front page of a paper that came out about 1.5 years ago on basically the difference between what climate change can actually say specifically about changes in drought and water supplies and what stakeholders need to know. And the main gap is it's hard to be specific about climate change because every water system, every water source is unique in how it's going to respond to climate change. And you can read this article. It's free access. Just Google my name and Earth's future, which is a fun search to do, I think. But I'm going to talk a little bit here about another paper that came out more recently, which looks at changes in water, surface water runoff, and soil moisture according to the latest climate model projections. Now, when we're dealing with drought, there's multiple factors affecting things. So it's not even as simple as, say, cold weather, where you've got rising temperatures and then maybe the weather patterns change. There's a lot of moving parts for drought. For example, things that would cause a trend toward drier conditions are rising temperatures, which lead to more rapid evaporation. Changes in rainfall extremes, if rainfall becomes more erratic on, say, a month-to-month basis or a year-to-year basis, then you would tend to have more frequent and intense droughts. And changes in rainfall seasonality, with the projections being that rainfall in the summertime may decrease more rapidly or rise less slowly than rainfall in other seasons of the year. And since summer is when we need the water, that can be a problem. On the other hand, climate change is affecting how plants use water. Increased carbon dioxide means they don't have to lose as much water vapor to take in the carbon they need to grow. So that would, all of the things being equal, lead to wetter conditions, and things would be wetter if carbon dioxide didn't also affect the climate. And then things that are a little more ambiguous, changes in annual precipitation. That's ambiguous because we've seen a historic increase in precipitation in Texas, but climate models don't project that to continue. So it's not clear how that's going to trend up or down in the future. Changes in rainfall extremes matter depending upon whether your drought is governed by runoff or soil moisture and groundwater recharge. Because if rainfall becomes more intense, given the same amount of rainfall, that means more water running off into reservoirs and streams, and less water soaking into the soil. So that sort of change has winners and losers. And then also, if all of these other factors affect the amount of plant cover, then that'll affect how rapidly plants are able to draw water out of the ground and into the atmosphere also. So here are the projections of precipitation and evaporation on an annual basis. The hatching indicates where 3/4 of the models agree on the direction of the trend. And in Texas, the projected trend is pretty small, but it tends toward the drying side for rainfall, which is on the left side here. On the right side, the trend in evaporation rates. You might expect that should be increasing dramatically because of higher temperatures, but this is actual evaporation. It's not potential evaporation. So you can't evaporate more than the amount of water that's supplied. So the trend is actually not very large because, especially in summertime when evaporation rates are largest, the amount of evaporation in Texas is limited by the amount of water available to evaporate. Now let's look at soil moisture. And here the trend, not just in Texas, but across the rest of the United States, is pretty clear from models that things should dry out. And it's both topsoil and deep soil. On the other hand, with runoff, the majority of models project an increase in runoff across Texas because of the increase of intensity of rainfall. But you notice the cross-hatching across all of Texas means it's somewhere between 50 to 75% of models projecting that. So the indications are favorable for increased runoff, but it's not a sure thing according to the climate models. Okay, lastly, we want to focus on really heavy rain, extreme rainfall that causes flooding. And this is some research that was funded by the Harris County Flood Control District and is going to be part of a paper that's going to be written by Savannah Jorgensen, my graduate student, and myself, that should be submitted within about a month or so. She's defending her master's thesis within the next month. And so we looked at, first off, just the amount of rainfall that's expected to occur on average once a century in any given 24-hour period. And we aggregated stations to get nice, smooth, broad estimates. And the 2 points out of this plot are, first off, if you're near the coast, you've got a bigger risk of extreme rainfall than if you're farther inland. That's true all the way from Texas to North Carolina. Second point is that the historic risk of extreme rainfall in southeast Texas, from Harris County to Beaumont, is higher than any place else in any other comparable location. And there's nothing really special geographically about southeast Texas compared to, say, Victoria or southern Louisiana. So at least a portion of that is probably due to, let's call it bad luck. Hurricane Harvey could have happened just about anywhere along the Gulf Coast, but it happened to occur in southeast Texas. And then Imelda occurred there as well, which was also one of the larger rainfall events in history along the Gulf Coast. So a little bit of bad luck there, unfortunately. For climate change purposes, we care a bit more about the trend. So here, to get this plot, we allowed the risk of extreme rainfall to change according to global average temperatures. And based on the historical trends, we see, generally speaking, at any given location, anywhere from a slight decrease to a large increase over the past several decades. The average values and the confidence interval are indicated by the blue bar on the right-hand side. So the best estimate here is about a 15% increase in extreme daily rainfall amounts over the past several decades. And that's averaged across all of the South and Southeast United States. Climate change should not be affecting one particular place differently from another particular place very much. So I think it's appropriate to just talk about an overall average trend in this region, because they're all influenced by the same sort of weather patterns, and climate change that be having a similar effect in all cases. And if you look at a climate model, well, they give you detailed patterns, but the model on the left is similar to the model on the right in terms of its model physics. But the details of the trends simulated by the models are very different from one place to another, which is the lesson there is you have to average together things. Okay, recently there was an evaluation by NOAA of the risk of extreme rainfall in Texas, and the estimates were significantly larger than the previous estimates in several parts of the state, indicated here by the green shading across Texas. Big increase in the estimated 100-year rainfall amount in Houston, in Austin, in San Antonio, and Del Rio. Now, I think the tendency is to assume that that's because of climate change. But again, climate change has a broad effect. So climate change is the reason there's more greens than oranges on this plot, the reason that there's been more of an increase than a decrease. But as for the details, that's probably a non-climatic effect. So again, for Houston and that area, they've been nailed by a lot of extreme rainfall recently that's gotten factored into the latest values, but not the previous ones. So that's why the Houston area is a bullseye here for the big change. The area from Austin across San Antonio to Del Rio, however, is more an effect of more information and more detail in the analysis. The blue lines on this plot are the old analysis, and you can see the old analysis didn't know about the Balcones Escarpment, didn't know about the Edwards Plateau, didn't know about Flash Flood Alley. The new analysis does, and that's why along the Balcones Escarpment, we have an analysis of an increased risk of flooding. So, well, the Houston lack of luck recently means that actually the assessed risk of extreme rainfall is basically comparable to what climate change has done probably and will do for a few decades. The assessed risk in Austin and San Antonio is still just keeping up with more detail, but is still based on the historic average, which doesn't take into account climate change. And I think for most of the state of Texas, the assessed risk in NOAA 14 is lower than the actual present day risk. Now, the NOAA folks recently came out with a report with recommendations on how to take climate change into account. It includes looking at historic trends, looking at model projections. I think some of their ideas are good, some of them not so much. Hopefully we'll be able to get things sorted out, but on the long term, actually be able to look at the present day and future risk of extreme rainfall, not just the past risk. Okay, so the basic takeaway lessons here. You can see each type of extreme weather is different, and they all have different aspects of how climate affects them. And for some of them, the existence of a trend is clear. There's good reasons for it. Temperature and extreme rainfall are like that. For others, such as drought, it's a more complicated picture. So thank you for your attention. I'll be happy to answer questions. And if you need to follow up, I got my email on the bottom of this slide.